we okay, so we take V tensor C of TT inverse, and we mod out it by the image of the operator D, where D is T tensor 1 plus 1 tensor Et. Okay, and so this is U prime, and for U of V, so it's U prime of V. And for U of V, one would take the tensor product with Laurent series. Okay, so now let us do the following. So we denote by AN the image of AT to the N, like this. So the bracket is given by AM B sub K is the sum over N, the binomial coefficient Mn. And now we have here A, N, B, and M plus N minus. Okay. And the theorem says that the bracket makes U prime of V into a lineage. U prime of V and U of V is okay. So this is the theorem. Okay, so now, the reason why these Lie algebras are of importance, well, there are many of them, but one of them is the representation theory of vertex operator algebras. So far we did not discuss it. So let's introduce the notation. But in short, so let me put the following kind of claim or idea that V or A modules correspond to U prime of V module. And you see, well, it's rather clear what is a module of a Lie algebra. And so it's more or less clear what one should check. But the representation theory of a vertex operator algebra is more involved. So you can somehow go in both directions and somehow use representation theory of Lie algebras or vertex operator algebras to study the objects you want. Okay, but first of all, we have to define what is the representation of a vertex operator algebra. And let us give a definition. Maybe do it here. Definition. Есть. Ну, там есть, so we have, for example, a joint representation, which is more or less the same vertex operator algebra. So, well, for example, the structure of a module of the adjoint representation is just the structure of vertex separated algebra. Yes, but what's the problem? Yes. Uh, 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 well, but I'm not sure it's possible. So I'm not sure that there are two different vertex separated algebras with the same u prime of v. Because you see, we have maybe hmm, well, but still, so I mean, I can't say. So we have only positive n here, so not everything is used in principle. But yeah. Absolutely, absolutely. Yeah, yeah. Thank you. Yes. So actually, I don't know. I don't know an example of two different vertex algebras with the same u prime of v, but might be. But then it would not be too surprising that they have the same representation theory. So the definition works as follows. So let v and then y0 t be a vertex separated algebra. So then M is called a V module if we are given map ym from V to endomorphism of M z plus minus 1. So note that it's the same y, but with the lower m here. So in other words, we're given the series ym az. Sum a n m t minus n minus 1 with the following properties. So the third thing is that y of ym 0z is the identity. The identity means that this is not a series, but just a single operator acting as an identity on M. And the second property somehow captures the structure of vertex separator algebra, namely for any A, B from V and C from M, the series ym a z ym bw c. Well, this kind of usual triple of series ym bw ym az c and ym of y a z minus w. Well, let me write. Sum z ym an b w z minus w plus 1 c. These are, as usual, expansion in w over z to the positive power. So these three guys are expansions of one series FAB C in M CW C inverse W inverse and Z minus W. So looks a bit frightening, but well, maybe I should write where do they sit. So let us do it together. So the first guy, where does it sit? So it's an element of what? What's the site? So this means that it should be Lorentz series in Z with coefficients being Lorentz series in W. Is it what we want?
Can I have a question?
Sure.
Do we require ym to be fields?
Yes, 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 yes. I should have written. Thank you. This is very important. Yeah. We'll get this. So it follows from this, but it's true. Yes. Well, there is a vacuum vector in the vertex operator algebra, but not necessarily in. So, is it correct? Once again, this would mean that the first line is a series, Lorentz series in Z, with coefficients being Lorentz series in W.
I think it should be Z and then W.
So replace or what?
Yes.
Actually, I also like it more. And actually, the reason is that, well, we first apply ym bw, yes? So this means that this guy is a Lorentz series in W. And then to each coefficient in this Lorentz series, we apply Ym of AC, making each coefficient a Lorentz series in Z, but not vice versa. Yes, that's how you can memorize it, but the reason is very simple, because actually this object is not Lorentz series in Z. So you can't have as many negative powers of Z as you want, because we first apply Ym, and you are getting Lorentz series in W, and then to each coefficient you apply such a thing. This may have infinitely many negative coefficients. Okay. By the same reason, this guy sits in M of W of Z. Okay. And the last one. Why?
The other way around, I think.
Irina is saying that it should be the other way around. So changing W and Z minus W.
Because for any for large enough n, it will be 0. So we have only finitely many terms in Z minus W.
Do you agree? Okay. So then what does the definition say? So okay, so there is so you have here infinitely many negative degrees of Z in principle, and infinitely many degree of W, but the vice versa here and something of this the sort here. But what does the claim say? It says that actually the poles in ZW and Z minus W, they are only bounded from below, right? So in principle, these are some complicated series in Z and W. But what you can do, for example, here, yes, you can expand. So for example, here you have 1 over Z minus W, and you can expand it to be here, or you can expand it to be here. And the only difference we allow between these two series is how you expand this guy in Z over W or in W over Z. And similar situation here, but so we have Z inverse, which can be expanded in W or over Z minus W or vice versa. So is it okay? So once again, it looks a bit strange, but actually we've seen such formulations before. But the claim is that actually this is a very strong condition, and we'll get from this many other properties, for example, locality and other properties. But of course, it's not that easy to check. Yeah, so if you're given some space and some operators Ym, then it's not that easy. Yeah, but so for that we'll get a reformulation. But this is somehow short way to formulate it in particular. So let me write remark from the very beginning. remark with saying that well, V is a module over itself, just Ym, V just Y. Okay, because we know that this is the OPE or associativity, yes, which does hold for the answer. Okay. Good. So, well, so once again, we're going to reformulate it, but before, let me also mention that. So remark. So we have natural notions of submodule, quotient module, irreducible module, etc. Yes, so since we are given operators acting in our space, then well, it's clear what does it mean to have a submodule or a quotient module or whatever. Okay. So now let's do a couple of computations. First of all, so this is the first proposition. No, well, there are some properties. We need some extra properties. So they are. It's easy to formulate them, but still something we'll say explicitly. Okay. So the first. Let's write it. One more remark. Maybe I even erase this. So actually two remarks. So assume let B tilde be a vertex operator subalgebra of V. So then V is a V tilde module with the same property that Y M is just Y. And another thing is that, so if W to V is a homomorphism of vertex operator algebras, then a V module becomes a W. Yeah, so it's a bit more general. So we don't have necessarily to consider a subalgebra with embedding, but just some homomorphism from one algebra to another, and then just kind of take the composition and you are done. and position. The proposition says that two parts. So the first part is that ym of TAZ is TZ. Ym is as you would expect. And the second thing is what Andrei already said, that all fields ym AZ are okay. So you see that we started with the locality, and this was kind of the main ingredient of the definition of a vertex separated algebra. Okay. This is the locality property, and in order to define a module, so we better use some version of the OPE of the associativity. However, here we work in an other direction, so we derive the locality from the associativity. Okay, so let's try to prove. So do you have any ideas how to prove the first part? So we have to use anyway this somehow strange and frightening definition. But how to use it? Mm-hmm. Yeah, so it's a good point. So we have to use somehow a vacuum. So let's do it. So let's take B to be a vacuum vector, okay, in the definition. And let's see what does the definition say. So then if B is a vacuum vector, then so the first thing is that so ym of AZ applied to C is what? Is expansion of one thing, the expansion, and another thing which gives the same is sum n from C ym n vacuum W over Z minus W n plus 1. So then let me write this equality, but I put it's not really the equality, but this means that they are expansions of the same thing. Okay. So now let's write this one. So what do we know about this guy? So what do we now know about AM0? Do you have any information? So n cannot be non-negative, right? So this is actually the sum over n greater than 0, ym a minus n minus 1, vacuum w, and here z minus w to the n. Okay. So yeah, so you see just one word that so this guy is an element in here, right? Because so I mean z minus w to the n is already non-negative thing. Yes, so it's just a series z w, and so here we have some series in w, right? And so how do we compare with this? So they have to be expansion of the same thing. So how can we use this? Mm-hmm. So can we write this one thing similar to such form? Mm-hmm. Yes, yes, that's also true. Let's write it. So this what? Mm-hmm. Yeah, it's because y of az to the vacuum is e to zt to the vacuum, right? Correct? Okay. So this we're going to use, for example, you see if n is 1, so the coefficient here in front of g minus w, just g minus w, is exactly what we want. Yes, so this is yes. Mhm. Which is equal to sum n greater than 0. Okay. So now the n equals 1. terms provide the desired equality. Okay. Um, because so this equality in quotes should be exactly the equality, yeah, because we don't have any well, so this guy, the left hand side is already the element in our space. Okay. Yes, now we have to prove part B. So we want to find n such that.
But haven't we already proved it when we discussed in the start locality? I mean, many weeks ago, we showed that the two fields are local when they are expand. Well, when we multiply them in the different order, it is an expansion of the same function, no?
Well, you see, we didn't have any module, so we were using the action of the operators just on the same space.
I think we just had two fields without vertex operator algebras. Two fields are local when we multiply them in the different directions. There's the expansion of the same function in two different ways. I think we had something like that, no?
Yes, that's true, but I think it was important for the proof that the fields, let's see, I don't remember what was the generality. Let us check. What was the generality? We proved it. No, I don't think we proved it in this way. So I think what we were doing, we were proving this for matrix coefficients. So we were saying that the two fields are local if and only if all matrix coefficients are expansions of the same thing. Well, this is very close, but not exactly the same, but very close. I agree. No, we just want it to be a series, yes? That's true. Yeah. So indeed, we have so there is an n such that such that c minus w to the n times f a b c c is in m cw c inverse w inverse. Okay, and but this is exactly the intersection of m cw with m w. Okay. Uh, uh, mm, right. Right, right. Mhm. So, how should we formulate it? Uh, uh, um, mm, mm, yes. So, let me write it. So, n does not depend on c, namely, it suffices to take n such that a n be 0 for n greater than. Okay. So therefore, then z minus w to the n as the commutator okay. So this means that all the fields are actually locked. Good. So this is done. And now so let me introduce a notation. I think we did it last time already, but nevertheless. So y of az be sum an z minus n minus 1. Okay, so note that we have square brackets instead of round brackets as we used to. And let me add one remark. So can you tell me what do we know about YTAC? Yeah, maybe I should write that this sits in U prime of V of Z plus minus 1. Okay. So what do we know about this series? minus z. Why? Yes, but sorry? Not exactly this equality. Let us write it in the correct way. Huh? No, it's very close to the correct equality. Let's do it completely correct. Mhm. But you're right, we more or less proved this. Mhm. So let's recall the definition. Yes? So what does it say? So what is this? This is the sum TA n z minus n minus 1. Yes, what is TA n?
We can use relation.
Sorry?
We can use relation in the definition.
Yes.
You
Yes, what does? So how, if we use it, what do we get? So what is the conclusion? No. Mhm. Okay. So it's important that here we do have this minus. And actually, this is the reason why we have plus here. Plus might write a minus plus, but we want exactly such a relation which absolutely coincides with the Brown bracket relation, yes, for the vertex operators. Okay. Good. Okay, so now since we have our u prime of v, and we decided that we want to consider some modules over this u prime of v. So let us give a definition. So u prime of v module M is called smooth if for any c or for any vector v in M, and A is A from V, A and M is maybe a better A and B is 0 for n large enough. Okay.
Is it square brackets or round?
Yes, yes, thank you. Square brackets. So do I need anything else? Probably not. Okay, and so, well, this is what we expect, yes, because so we know this property for fields, and since the representations are somehow sorry? As if so indeed, so mark this is equivalent to y. Well, I mean, so far, okay. So let me write ym az acts as a field on M. Okay, so this is the first ingredient we really need, and in order to somehow relate the V modules and U prime of V modules, we need one more condition, which is formulated in terms of normal ordering. And let's kind of more or less repeat the definition of normal ordering for this square bracket notation. So definition AB from V, we can write normal ordered product YAZ YBW. So can you tell me what's that? No, just definition. So let's write something like so what do I put here and there? No. Yes. No. Okay. So this is the standard definition as we had before. Okay. And So the reason why someone's lemma, again, the usual one that YAZ, YBZ is well defined on a smooth module. Yes. Well, no, it is a field also, but it is just a well-defined, the first claim. So because, yeah, because you see we have the same variable here, and the proof is just the same as before. Okay, and so now the thing we want to assume. So U prime module, now the definition. M is called coherent if first M is smooth. Second, Ym of AZ equals to well, applied to the vacuum equals to A plus Z times something.
Ym of AZ, it means we have Y of AZ and then we apply it to M, yes? Because I'm not sure we had this notation. Or square
Right.
brackets.
Right. Well, you're right. So we have such a series. Yes, and then each. So I mean, maybe we can even not write this, but this is just to say that these operators, so these elements of U prime of V, are now considered as operators acting on our vector space M. Okay.
And what is vacuum vector here?
Oh. No. This is, what did I want to write? Sorry. Yes, I wanted to put it inside, but I think we already said it for smooth. Did we? So when defining smooth, did we say something about the vacuum vector? Where is the definition of the smooth? No, we did not. So I'm sorry. Just like this. Thank you very much. So we don't have vacuum in the module. So what I wrote before was the kind of axiom for vertex parity algebra. But for arbitrary M, we don't have a vacuum vector, and therefore we can only use this vacuum inside Y, and this is what we do assume. So that if you take this vacuum vector inside, and you get the identity. And the last thing is that we take Ym square brackets, and we have A minus 1B of Z. So what should it be? Can you tell me? So what do we expect? Well, I mean, we want to write some definition, but so this should be somehow similar to what we have in a vertex algebra itself. Well, let me ask you, if we I mean, if we had no m here and round brackets, what would we have? So if we just had a vertex separated algebra, but do you remember the reconstruction theorem? What does it say?
It should be ordered product of YAZ and YBZ.
Mhm. Oh. Where is m? It's -1. So we will get arbitrary thing here. So this can be deduced easily, actually, because we don't know how t acts. But so it's enough to say this. Absolutely. Why don't we say it right away? So lemma for a coherent module y of a minus m b equals to what?
And factorial, no?
Yes.
And again, I think it should be square brackets on the left.
I hope they are square, but
I mean at the a minus m should be square brackets.
no, because we can't apply a square bracket to the element, right? So this is the and so both a and b are from V. Therefore, we can't. So we do have. So this a square bracket is an element of U prime of V, but this is the operator acting on B itself. Okay. Does this make sense? Irina?
Yes.
Okay. Sergey? All right. And this just follows from this TA. Okay. Okay. Another theorem says that, as you can guess, that V modules are in one-to-one correspondence with U prime of V modules coherent. Okay. And actually, well, it's very easy to say how do we want to construct such a correspondence. Yes, so if M is a V module, so then we produce U of V module structure on V on M by how? So we have a module M. How do we produce the structure of U prime of V module? Absolutely. Yes. By definition, and vice versa, if M is a coherent U prime of V module, then M is a, well, we define YM AZ by definition by YM AZ. Of course, yeah, of course, there are many Y's here, so and we have to prove. So it's not a proof of the theorem, of course, but this is the correspondence. Yes, so this is what we want. And now, of course, we have to prove in both sides. Yes, so this is absolutely non-trivial. So so first, from V module to U prime. Yes, so we start with the module over the vertex operator algebra, and then we proceed with the module over U prime. Yes, so what actually do we have to show? So we are given the operators corresponding to AN. Yes, so we have this YM. Yes, YM are given. And then we proceed, we define this square bracketed. And so what do we have to check?
Something about the bracket.
Of course. So actually, this is the second thing, but let me write it. So we have to check that A M B K is some n greater than 0 and n A and B m plus k minus n. Oops. Like this. So, but this is the second thing. There's more kind of basic thing we have to check. Yeah, but I should stress that maybe I put M here. Yes. Oops, no, I don't put. Yeah, well, yes, just 1 minute, but I just claim that there's one more, even more basic thing we have to check. Well, this is also true. So the coherence. But no, okay, let me. What I want to say, I want to say that we have to check that A M n equals to minus n A M n minus 1. Because otherwise we cannot factor through what we have to factor. Yes. Well, I mean, by definition, our U prime of V is V of TT inverse modulo image of T, right? So far, the definition, how we write it here, we say that the A with the square bracket n acts as A with the normal brackets, round brackets, say n. Okay. And then the third thing is that the coherence conditions. Say it again, what composition do you mean? Well, we have a map, but what kind of map? So you see, for each A from V, we can construct the elements A n. So in a sense, there are many elements attached to an element from V. So this is actually the idea of this U prime of V. Yes, so you somehow take an element from V, and then you somehow duplicate even more. You take many elements of this form. But then we have to show that some conditions are actually satisfied. For example, in order to be able to say that U prime of V acts, so we need to check this one. So do you agree? Or still something is wrong? So is it, for example, is this clear? well, this would mean that we have a map from, so what we want is a map from u prime of v to and v and l, right? This is what we want. And this should be a map of Lie algebras, right? And the map is given by an maps to a n m. So this is our definition. So, but so far it's even not clear why this definition is well defined. Because we have this quote. And this would say us that there is such a map of linear spaces. Yes. Actually, I'm claiming that it is on the board. This statement is on one of the boards now. On the boards here. These are our boards, and I claim that this statement is on one of the 4 boards. На доске. Утверждение на доске написано. Надо понять, на какой, и найти.
It should be something about T, obviously.
Yeah, exactly. Yes. This is equivalent. Yeah. So this claim is equivalent to what is written here. It's just a generating function of this. We start with the module of V, and we want to construct a module of U prime. And this is the definition. Да, на другой носке. The second is this one, but this is for square brackets. This is exactly what we want to check. And indeed, since we have such a definition, we need the same claim for round brackets. Konstantin is saying that we do have it here. But actually, this is part A of the proposition. Here? No, because we want a module. Of course, no. I mean, if we write here round brackets, this is true. But our goal is somehow to we defined these operators by such a formula. This is the definition. Yeah? The definition of the action of U prime of V. Okay. Yes. And so this is the definition. Now for this definition, we have to check that something holds true. Okay. So what about this one? Yeah. So of course, some details have to be worked out, but actually, you remember we proved such an equality for round brackets using the OPE formula. And actually, we do have OPE for the fields acting on. Yes. Well, I don't think it's good. We'll do it now, but just we'll add some details next time. And the last thing is also quite transparent. Comes from the reconstruction theory. Okay, and of course we need to do the other way around. Okay, let us stop now. So any questions?
Вы сказали, что второе тоже верно для круглых скобок?
Вот это?
Нет,
вот это.
вот это, да. Оно верно для круглых скобок?
Да. Вот тут написано. Вот. Yeah, I don't know. Yeah, I understand the question, but I don't know. Maybe coherence means that it is compatible with the structure. For example, I can give you some example right away. So, for example, you know the SL2 hat? SL2 hat, yes?
Yes, there is two models.
On level 1, for example. So I mean, there is a so we discussed that for SL2 hat, there is a structure of vertex operator algebra on the vacuum parabolic Fermat module. Yes. So there is a quotient vertex operator algebra on irreducible module. On irreducible, for example, level 1 module vacuum. So I don't know. Do you know about integrable representations of SL2 hat? So, for example, you can get modules over affine algebras using the representation theory of affine algebras. It's not. It's yeah. It's no level. So, for example, level 1. Okay, maybe let me give you a simpler example. So you explained us about the lattice, and so there is this lattice vertex operator algebras. We didn't discuss it yet, but okay, maybe I better write it in May and more details. But so there are some examples coming, for example, from lattice vertex operator algebras or from Kac-Moody. But they're not very simple, of course. What kind of special properties? Well, for some vertex operator algebras, it is true, but not for all. Если успеем. У нас 2 занятия выпадает. Или 1.
А переносить мы их не будем?
Вот это вопрос. Значит, смотрите, у нас есть третье число, которое, видимо, выпадает. А можно, наверное, выключить.